There we go.
That's pretty cool. Good explanation. You can just walk first. Okay, I'm going to wait it. Okay, I'm going to put that on my list too. I mean, it's a great movie regardless.
It's a good movie.
All right.
All right, good morning, everybody. So today we were supposed to do an inverted lecture, but what I've decided to do is we're going to put that off until Monday. And so we're going to finish up Chapter 7, doing some work on the board and talking about some topics. I just figured it would probably work better that we not start a new topic on Monday. We'll do the inverted lecture. We'll be able to catch up without much issue because there's actually a built-in day on catch up at some point. So we'll just catch up at that point. So it's nothing for you all to worry about. So we'll work some problems today and we'll go from there, okay? Does that sound fair? Just to remind you all, your video lecture or video projects are due today by 5 o'clock. So make sure that I get them. So if you sent them, you think there's something wrong, you can send it again. Okay, by 5 o'clock, that's the cutoff time. So in Chapter 7, we've been talking about eliminations where we are taking something like an alkyl halide and eliminating HCl or HBr or HI, whatever the case may be, to get a alkene. And in this case, we used bases to do this reaction, right? And we can have E1 and E2 type eliminations, right? If it's an E2 elimination, how does the hydrogen have to be with respect to the leaving group? Anti-periplanar, right? And so we know that. So we have to have an anti-periplanar arrangement in the mechanism. Well, we're not limited to alkyl halides in elimination chemistry to get alkenes. We can also use alcohols. So for example, we could take something like ethanol and we can eliminate water and get ethene in this case. Okay? What do you think we need as a reagent to do this type of chemistry? Do we need an acid or a base here? We need an acid in this case. Bases don't work very well here because hydroxide is a poor leaving group. Okay? Hydroxide is not a particularly good leaving group. And so bases are out of the question, and so we need some type of acid. And one acid that is everybody's favorite to use in these types of reactions is sulfuric acid, concentrated sulfuric acid. Okay? Where else might you come into contact with sulfuric acid in your everyday life? Also has another name called battery acid. Car batteries. Car batteries have, by and large, although some new car batteries these days don't use lead acid batteries, but lead acid batteries is another place where you'll find sulfuric acid. Okay? Now it turns out that you need to heat this reaction, and delta, just means heat. It's not cyclopropane, it's delta over the arrow, so we're going to have to heat this. And quite frequently we have to heat this particular reaction to about 180 degrees Celsius. So it's a pretty high temperature reaction that you have to do. And so we can eliminate water from this and get an alkene. Okay? We can also use other acids. So for example, we can take a secondary alcohol and phosphoric acid, concentrated phosphoric acid in some heat. This is about 150 or so degrees Celsius. And we can get our alkene and water. Okay. We can also do the same type of chemistry with a tertiary alcohol. So for example, tert-butanol. And we can use a different acid, in this case, an organic acid. Okay. And we'll heat this to about, this is somewhere around, 80 to 90 degrees, something like that. And we will get our alkene plus water. Okay? These are the three acids that I need you to commit to memory. Concentrated sulfuric acid, concentrated phosphoric acid, and this organic acid, which is abbreviated as PTSOH. Stands for para-toluene sulfonic acid. And all you really need to know is that it's an organic derivative of sulfuric acid. It's about the same acid strength, more or less, as sulfuric acid. Okay, it's a very strong acid. Concentrated sulfuric acid, concentrated phosphoric acid, and para-toluene sulfonic acid are also known as dehydrating acids. They will remove water from organic molecules very, very easily.
SO3H.
SO3H. You all may have seen a demonstration of this before. Maybe. Okay, I can't do it in here because it puts off a lot of steam and working with the strong acids, I can't do the demonstration. But you can YouTube it. You can take a beaker full of sugar and you can pour concentrated sulfuric acid in it, and it gets really, really hot. Steam starts to come out, and then all of a sudden this big black snake starts coming out of the beaker. You've seen that? Yeah. And so that big black snake that's coming out is nothing but pure carbon. So what is sugar? It's also known as a what? A carbo what?
Hydrate.
Carbohydrate. What does that name literally mean? No, that would be hydrocarbon. But what does carbohydrate literally mean?
Carbon with water in it.
That's it. And that's all sugars are. They are nothing more than a mixture of water and carbon, literally. And sulfuric acid, concentrated phosphoric acid, para-toluene sulfonic acid can dehydrate those, and actually what you end up with then is that pure carbon coming out. That big. A lot of smoke, stinks, but it's a pretty good demonstration. Okay? And so what it's doing is it's generating carbon in the process. Do you suppose the mechanisms for all three of these are the same? We're removing water from both of them, right? So it's the same type of reaction, but in fact the mechanisms can actually be quite different depending on the type of alcohol that you have. What kind of alcohol is this? Primary, secondary, tertiary? Primary. How about this?
Secondary.
All right, so let's look at what's happening in these reactions. Let's look at the mechanism. The first step in all three cases is going to be identical, so that's going to make life easy. So let's start with the primary alcohol, in this case ethanol. I place it into concentrated sulfuric acid, and I'm going to heat it up. Heating, we know, favors the elimination reaction, right? So we know that, so that's good. What do you think the first step is here? I've got a strong acid and I've got an alcohol. What do you think is going to happen first? What do acids like to react with? Bases. Do I have a base? I do. The oxygen atom of the alcohol can function as a base, can't it? Is sulfuric acid a strong acid or a weak acid? It's a strong acid. And so what I like to think of it as, and I do this admittedly to make my life easier, I like to think of it as a mixture of H plus and HSO4 minus. Strong acids dissociate, right? And water? Well, alcohol is nothing more than organic water. Why shouldn't it dissociate, right? Reasonable enough. So what's the first step? How am I going to push arrows? What's going to happen? If acids like to react with bases, how's that reaction going to occur?
The molecules of the oxygen are going to pick up the other nitrogen.
You're going to pick up the what?
The proton.
And this is actually a reversible step. We need to draw it both ways. Everything is balanced, right? And so this is our protonated alcohol. The alcohol gets protonated. It kind of looks like what? Sort of looks like water, doesn't it? It absolutely sort of looks like water. So now what happens? Is water a good leaving group? It is. Water is a good leaving group. Can that just leave?
No.
No. And why not? If it left, we'd generate a carbocation, correct? What kind of carbocation would I generate here? Primary, secondary, or tertiary? Primary. Are primary carbocation stable? No. So we're not going to have a primary carbocation intermediate. But what can happen? Got some beta hydrogens, don't I? I'm going to just pick on those three and actually show them so you can see the beta hydrogens. Right? So this is the alpha carbon. Right? This is the beta carbon. So if I can't generate a carbocation, this can't be E1, can it? So it must be E2. So what's happening? What happens in an E2 reaction? Okay. Give me more. You're right. What bonds do I need to make and what bonds do I need to break?
There needs to be a double bond between the alpha and beta carbon.
Okay, I need to put a double bond here. Where am I going to get those electrons?
When the bond between the carbon and the oxygen breaks.
So if this bond breaks, how does that make a pi bond? Because it's taking electrons with it. It's part of it, but where do the electrons come from the pi bond? It's not going to be these electrons.
Isn't there still a lone pair electron in the oxygen?
There is one, yeah. But they can't become the pi bond because they got to leave with the water, right? All of this is going to go with the leaving group. Where are the electrons coming from for the pi bond?
When you break off the oxygen, there's a lone pair on the carbon.
Nope.
No?
CH bonds.
It's the CH bonds, right? So one of these pairs of electrons is going to become the pi bond. Right? So how do I get rid of that hydrogen? In an E2 elimination, what do I have to have? What do you think, Jack?
Not thinking fast.
You're not thinking fast?
This is not thinking fast.
Oh.
Wait, so how does the CH bond break?
Yeah, how does it break? In an E2 reaction, right, we have to have, or at least when we were talking about it before, we had to have the alkyl halide and a base, right? Well, now we don't have an alkyl halide, but we've got a leaving group that's going to be like a halogen, water. We've got the CH bond. Where's our base? The HSO4 minus. It's our base, right? So how does that happen now? How do I push the arrows?
It extracts the hydrogen.
Right. Plus water plus H2SO4. Now wait a second, I started with H2SO4, I end up with H2SO4, so sulfuric acid is what in this reaction? It's sort of a spectator, but that's not what we would call it here. It's a catalyst. It's not consumed in the reaction. This is an acid-catalyzed dehydration of an alcohol. I do not need to have a ton of acid around for this to occur. Okay? Now, we're doing this at 180 degrees. Okay? This is a gas at 180 degrees. This is gas at room temperature. This is a gas at 180 degrees. So notice I did not make this a reversible arrow. Whose principle is responsible for me not drawing this as a reversible arrow? Le Chatelier's principle, because I am removing products as the reaction is occurring. And so the reaction will lie to the left or the right? To the right. Chatelier's principle dictates that, right? Okay. So this is what kind of elimination? E what? E2, right? This is an E2 elimination of an alcohol, or of water from an alcohol, excuse me. Okay? So primary alcohols, E2. Tertiary alcohols are E1. So we're starting off with our tert-butanol, sulfuric acid. Again, we think of that as H plus and HSO4 minus. The first step is identical. We're going to protonate that alcohol. So how would I push the electrons?
To the proton.
To the proton from?
The oxygen.
From the oxygen lone pair to the proton. I end up with the protonated alcohol. That is a reversible step. Now what can happen? We're going to generate a carbocation. Water leaves in the slow step. I generate a carbocation plus water. That is perfectly reversible, right? Plus HSO4 minus. Now what happens? What do you think happens now, Caitlin? I've generated a carbocation, right? I've got water and I've got HSO4 minus. What do you think is going to happen now? If water attacks the carbocation, it just goes back to the starting material, right? And that can happen. But sometimes the water bumps into what? Maybe it doesn't bump into the carbocation. Maybe it bumps into one of those hydrogens, right? Then what happens? And I'm just going to put one hydrogen here. And we end up with our alkene plus H3O plus HSO4 minus, just to keep everything balanced. H3O plus and HSO4 minus is sulfuric acid. It too is catalytic in the sulfuric acid, right? And so this is an E1 mechanism. It has a carbocation intermediate. This one up at the top, primary, is an E2 mechanism. It does not have a carbocation intermediate. The reaction here is dependent on the concentration of the alcohol and on the concentration of the acid, right? This one, it is only dependent on the concentration of the alcohol. What about a secondary alcohol? Is it going to be E1 or E2? What was it when we had a secondary alkyl halide? It depends. And it depends here as well. Okay, however, I will say this, that secondary alcohols, in my experience and all the things that I've studied in the past, typically undergo E1 elimination. Because, in part, you're heating the reactions. Okay, you have to heat these to get these to go really well. And it seems that the chemistry, by and large, seems to follow E1 chemistry, not E2 chemistry. But both are technically possible.
On the tertiary, why would the electron pair from the oxygen attack the hydrogen instead of the negative charge?
You mean the positive charge?
Or the negative on the HSO4?
Well, think about it. HSO4 minus is a stable conjugate base, right? So when you take sulfuric acid and you place it into water, it dissociates into H plus and HSO4 minus. It's perfectly happy that way. So the water's not going to protonate the HSO4 minus to make sulfuric acid again. That would go from a weaker acid to a stronger acid, and that's not how equilibria lie, right?
Yes, sir.
They always lie from stronger to weaker. So that's the reason why.
Yes, sir.
Does that make sense?
Yes, sir.
Now let's look at an example. Where I take a secondary alcohol and I'm going to place this in sulfuric acid. And what I want to get is that alkene. So I have Kaylin and Jack going to the lab, they get this alcohol, they take my sulfuric acid, they mix it together, they do the chemistry, they go back, analyze the product, and what they find is they don't have that alkene. They did not generate this at all. And in fact, what they find is they get this alkene in high yield. It's not a minor product. It's 99% of the product. We have to explain what happened. Now, looking at that, what can you tell me happened?
A methyl group.
We had something move, right? And it was a methyl group, okay? And it turns out that there is a rule for carbocations, and I call it the cardinal rule of carbocation chemistry. And that is that if a carbocation can rearrange to a more stable carbocation, it will. You will rarely hear me be this definitive about things. Anytime you generate a secondary any carbocation, but especially secondaries, you need to stop, pause, and think hard about it. And you need to ask yourself, can that carbocation rearrange to something more stable, to a carbocation that's more stable? If the answer to that question is yes, do it. Okay? So let's see how this happens. So Ahmed, what's going to be the first step? I've got an alcohol and I've got a strong acid. What's going to be the first step?
Lone pair of electrons from the oxygen.
Okay, so I'm going to protonate that alcohol. Right? So the lone pair. This is going to be a reversible step. This is a secondary protonated alcohol. The water can leave and leave me with a secondary carbocation, can't it? Secondary carbocations are okay. So I'm going to draw this as reversible. Is secondary the most stable carbocation? It is not. What would be the most stable carbocation? Tertiary. Can I move something in such a way to get a tertiary carbocation? The answer to that question is yes. I can have what's called a methyl shift. I can shift just about anything I want. I can shift hydrogen, I can shift alkyl groups, I can even do ring expansions, which we'll see in a moment. I can move rings around. Okay? And this is one of the cool things about this chemistry. When you are looking at a secondary carbocation and you have an adjacent carbon atom on one of the beta carbons with something that can move that would generate a more stable carbocation, move it. Okay? Now, carbocation rearrangements are going to be your bane. They're going to drive you crazy. You will throw your hands up in frustration with them, and I do as well, because they can get in the way of all kinds of things you want to do. But one of the things that you can do that makes it easier for you to deal with them is to number your carbons so you know what's moving and where it's moving to. And I don't care how you number your carbons, okay? But just number them and number them consistently. 1, 2, 3, 4, 5, 6. Okay? Now these three methyl groups are all equivalent, so it doesn't matter which one you move. But what I'm going to do is I'm going to move carbon number 6 over to carbon number 2. Okay? And the way that that happens is I've got these electrons in this bond, right? The electrons migrate to carbon number 2. And when they do, they move the methyl group with them. So I have a carbon 6, carbon 3 bond, but now how am I going to have it bound over here? It's going to be a carbon 6, carbon 2 bond. That little arrow with the curlicue means rearrangement. So when you see that, that means we're doing some type of rearrangement in chemistry. You have a question? Oh, okay. So, 1, 2, 3, 4, 5, there's 6. Where's the carbocation now? It was on 2. Where is it now? It just doesn't disappear. Where did it go? Went to carbon 3, right? And now I have a tertiary carbocation. Is that more stable than the secondary? You bet. And so that happens. These carbocation rearrangements are extraordinarily fast. They happen almost instantaneously. Now what happens? I've got water. It came off this, right? I needed to draw that in. Be accurate. So now what happens? It does. Which one? Are all beta carbons the same here? They are not. Which beta carbons do I have? Give me the numbers.
5, 4, and 2.
5, 4, and 2. Whose rule do we need to use now? Zaitsev's rule. What does Zaitsev's rule tell me? Okay, so which one is that? 2. So the main product will be where the water comes in and abstracts the hydrogen from carbon number 2. I generate the alkene, and I get my H3O plus back, right? And so this 2 is acid catalyzed. I get started with acid, I get acid. Okay? That is a carbocation rearrangement. Anytime, I'm going to repeat it again, and please listen to me. Anytime you generate a carbocation, I don't care how you generate it. It doesn't matter if it's an elimination reaction, a substitution reaction, whatever. When you generate a carbocation, pause and think about it. Can that carbocation rearrange to a more stable carbocation? And if you say in your mind, yes, do it. Okay? We're going to do it. So we know that primary alcohols, no carbocations. Tertiary alcohols, carbocations for sure. Secondary are going to be somewhere in the middle. But with this elimination chemistry, especially with the alcohols, because we have to heat them up, secondary alcohols more often than not give you a carbocation intermediate. And so you're going to have to pay attention to rearrangements. Okay? So, seems like we're stuck, doesn't it? I can't make the alkene that I want. So Holly, I really need that alkene for something in my lab. I had a bunch of this around, but it looks like I can't do that to make it, right? So how can I overcome this problem? How can I get that alkene that I need to do my chemistry? I'm asking you to solve the problem for me. How am I going to solve that problem? Obviously, I can't use that alcohol, right?
Right.
So how can I solve this problem? I need that alkene. What tools do I have in my toolbox? How can I solve this problem?
If you heat it up, wouldn't that get rid of the water as it comes out? Like, what would be the E2 here?
So you're suggesting to go through an E2 process. That's not a bad thought, but heating it up won't do it. Because secondary alcohol will give me a carbocation intermediate, which would be hard to control that. How can I solve the problem? I could change the alcohol. I could.
You could put the hydroxyl group on the primary carbon.
On the primary carbon. Okay, let's go down that rabbit hole. Let's see where that gets us. So Savannah's suggestion is to start with that alcohol. I can't generate a primary carbocation, can I? And so her suggestion would be to take that primary alcohol, heat it up in sulfuric acid, and try to get that alkene. But when I do that, so I have Savannah go do that, so she solved my problem, at least we hope. She goes and runs the reaction, and lo and behold, she comes back, and she gets the same alkene that Jack and Kaylin got. What happened? I thought I couldn't generate a primary carbocation. What do you think happened, Nana? It turns out Savannah was half right. The first product that she gets actually is from an E2 elimination. And she gets this. But in the presence of a strong acid, an alkene is actually a base. And it generated the secondary carbocation, which then rearranged and then eliminated. So, good idea, halfway right, still gave me the product and the problem. So what can I do? The answer is so obvious you're missing it. Don't use an alcohol. So what other solution do I have for eliminations if I can't use the alcohol? I can use some type of alkyl halide, right? So what I would do is I would start off, I don't know, with that bromide, and I would force it to do an E2 elimination with a base, like sodium ethoxide or something. Okay? We would get the base, acid-base chemistry to go that route. That's the only way that I could practically, at least as far as I know right now, with the tools that we've learned in this class, to do that type of chemistry. It would be very difficult to do that with an alcohol. I would need to use an alkyl halide. Okay? Now there's chemistry that we're going to learn in another chapter of how we can take alcohols and convert them into alkyl halides, and we could do that kind of chemistry first, and then do the elimination. Okay? But you see why we have to have access to multiple functional groups? Because the products that I want, even though it looks simple, sometimes I'm limited by the chemistry that I can do with particular functional groups. Alcohols, either the secondary or primary alcohol, would end up giving me the same product. And that's a problem, right? Because we know something about the mechanism. I'm going to give you a couple of, a minute or two here. I want you to figure out what happens when I heat this up in sulfuric acid. What product do I get? We all
Rapidly dying.
slower the better. When you look at that problem, what's going to happen? We're going to get something shifting, but before we even get to that level of detail, what's going to happen? I'm going to convert an alcohol into what? and my organic part. An alkene. How do I know that? I know that because I've got an alcohol and I've got a dehydrating acid. I know I'm going to convert an alcohol into an alkene. So on an exam, if I don't have it, things that aren't alkenes can't be the answer, right? So we can use some test taking skills there. But I am going to have a shift here. Okay? Now I'm going to number my carbons 1, 2, 3, 4, 5, 6, 7, and 8. The first step is going to be protonation of the alcohol. I know that that's going to occur. 1, 2, 3, 4, 5, 6, 7, 8. Keep track of everything, right? So, right, that's what happened. Now what happens?
Electrons from the carbon-oxygen bond go to the
Okay. Water leaves.
one of these, and that forms a secondary carbocation.
So I generate a secondary carbocation. Very good. So I'm going to write down here that it's secondary. I'm like 1, 2, 3, 4, 5, 6, 7, 8. All right, now what happens? Yeah.
Well, I was just wondering how you would know whether or not you have a methyl shift or like a hydrogen shift.
Okay, we'll talk about that. That's what we're talk about now. What happens next? Just pick one. What happens? Pardon?
Carbon 8.
Carbon 8? Okay, so if carbon 8 shifts, right, so the carbon 8, carbon 3 bond moves over and bonds to carbon 2, so now we have an 8-2 bond, right? So I'm going to use my little curly Q arrow, and I'm going to put that there. I'm going to put that carbocation there. So that's carbon number 8, that's carbon 1, that's carbon 2, there's 3, 4, 5, 6, 7. What kind of carbocation do I have? Tertiary. All right. There's another possible shift. What is it? Can I have a hydrogen shift? On this carbon there are no hydrogens, right?
Right.
There are only hydrogens on this beta carbon. If the hydrogen shifts here, I'd end up with a primary carbocation, which I know I can't have. So hydrogen shift, or hydride shift as we call it, is not possible here. But I have other alkyl groups. It's just part of a ring, right? I can shift carbon number 4 over to carbon number 2, which would be the same as shifting carbon number 7, but I like 4, so I'm going to pick on 4. It's an even number. All right? So another possibility would be for carbon 4 to shift over. And in doing that, right, so if this is 4, this is 2, 5, 6, 7, so 4 to 2, this would be 3, 7 to 3, yeah, and then I've got 1. So 1, 2, and where's my carbocation now? If I'm moving the electron from the 3-4 bond to make a 2-4 bond, the carbocation now has to reside on carbon number 3. What kind of carbocation is that one? That is tertiary. Uh-oh, I've got 2 tertiary carbocations that are possibilities. Which one is it going to be? What do you know about the structure of a carbocation?
Missing a bond.
Huh?
It's missing a bond, electron pair.
Okay. What do we know about the structure of a carbocation? Tell me something about it. What shape is it? It's trigonal planar. What are the bond angles? 120, right? This one will have 120 degree bond angles because it's part of a 6-membered ring. How about that one? It is not going to have 120 degree bond angle. So which one of these carbocations is the most stable? The bottom one. So this is a situation where ring strain, because a 5-membered ring is strained a little bit, not a lot actually, but it's strained enough such that it's going to actually ring expand, and we're going to go from a 5-membered ring to a 6-membered ring. And now, right, my water comes in, abstracts the hydrogen, and I end up with this alkene. When you're looking at carbocation rearrangement, do not just look at the first rearrangement that's possible. Look at all of them. In this case, 2 things could have shifted, both giving tertiary carbocations. But we had to think deeper than that, right? We had to recognize that the carbocation wants to be trigonal planar with 120 degree bond angles, and only one of them could give that. You can actually have a situation where a secondary carbocation is formed. So you go from a secondary to a secondary. And you go, well, why would it do that? Because it's relieving ring strain. There are some examples in your book that show you that you can go from a secondary to a secondary without much trouble. Okay? All right. It goes without saying you all have to practice these alkyl shifts and these hydride shifts to be good at it. It will take practice. Number your carbons, build your models, okay? Know how things are being formed and broken. We can also do elimination chemistry to generate alkynes, so carbon-carbon triple bonds. So pH just stands for benzene ring. I can take this dihalide and I can eliminate HBr twice to get the carbon-carbon triple bond. Oops. I'm just doing an elimination twice. However, in these types of eliminations, you need a stronger base than what we've used before. Before, we've used things like potassium terbutoxide, we've used sodium hydroxide, we've used DBU and DBN. Those bases will not do this chemistry under normal conditions. We need something much stronger. And that much stronger thing is sodium amide. It is a base that has a pK of around 35-ish, 34, 35. The reaction is quite frequently done in liquid ammonia. And this is usually present in excess, so you add an excess of it. And I abbreviate excess as XS. Okay? The mechanism for this reaction is actually quite simple. The amide comes in and abstracts a hydrogen. Leaving group leaves, so it looks like an E what elimination? E1 or E2? E2, right? I get an alkene that bears a halogen and a hydrogen. Okay? This has to happen a second time, and this time it's not as easy to eliminate. That's why we need a really strong base. And so now another equivalent of amide comes in and does the second elimination. This is known as a vicinal dihalide because the halogens are on adjacent carbons, but it also works for geminal dihalides. What's a geminal dihalide? It's where the halogens actually share the same carbon. Okay? Is this alkene, cis, or trans? Can you define it as cis or trans? We can't define this when it's cis or trans. We need another nomenclature. Does anybody know what it is from your reading? E versus Z, right? And so what you do is you find each carbon and you assign priorities. Hydrogen and carbon, which one has the highest priority? Carbon. So I just use H and L for high priority, low priority. Here we have a carbon and bromine. Which one takes the highest priority? So I look at the two high priority groups. I notice that they're on the same side. Z. Z is on the same side. Another corny little thing. E is like trans. Okay. Z is like cis. But cis and trans doesn't work here, so we have to have this E and Z nomenclature. All right, we've got some more stuff to cover. We're going to get started on addition chemistry. I'm going to work some of this out and get it on a screencast. Maybe I'll throw it at the end of this lecture. I'll probably have that up tomorrow, so you'll see something from me about that. For those of you who want to pick up your exam to redo for Monday, I've brought some of those exams with me. I think most of you have already picked it up, but if you haven't, I've got those. And have a great fall break.